Hi folks, in this video we are going to be looking at covalent bonding, the different types, shapes of molecules that covalent substances can have, and a little quick summary on conductivity. So covalent bonds form between two non-metal atoms. So why is that? So atoms either want to have a filled outer shell of electrons, so they'll do that by either gaining or losing electrons to achieve that full outer shell. Feel free to go back and have a look at electron arrangements and atomic structure if you're not sure what I mean. So the atoms either want 2 electrons in the outer shell, if they are one of the first few elements, or they want 8 electrons in the outer shell. So covalent bonds do this when the non-metal atoms, they share their electrons, which gives both atoms a full outer shell. So they're held together by their common attraction for that shared pair of electrons. So we can draw some diagrams to help explain this. Let's go for fluorine. So fluorine's got the electron arrangement 2, 8, sorry, no it doesn't, it has 2, 7. It wants to be 2, 8. So it's going to bond with, let's go for hydrogen, which has the electron arrangement of 1. So it wants to bond to have another one to be 2. So let's draw a circle. Here for fluorine, let's make it a bit better circle. And we'll put an F in the middle for fluorine. So what you need to do is you need to fill your electrons up around the side. So from earlier, you know that electrons fill up on their own, like this, before they pair off to... So that's me drawing 7. Now as you can see, there's a little gap here. And that's where that hydrogen is going to bond. So if we take our hydrogen, so we draw overlapping, and we draw a little circle here overlapping, that is hydrogen's got 2 outer electrons and fluorine's got 2 outer electrons. In this little gap here, that's where they share electrons. You can draw other examples as well, depending on the different shape. So let's have a look at water. So we know water is H2O, and oxygen you'll find has 6 outer electrons. So let's fill it in. 1, 2. So there's 2 gaps. And if we go back up to hydrogen, we know hydrogen's got 1 outer electron. So that's why there's 2 hydrogens. So we can pop one here and join it up here and here again and join it together. And that's how we make our shape of water. Hopefully when you saw me drawing water, you would have noticed that it was slightly different from the first example that I drew. Now that can be explained by looking at the different shapes that covalent molecules can form. So here we have 4 different pictures with 4 different molecules, and we're going to talk about the shape of them. So the first one here, we have oxygen. Now oxygen is something called a diatomic molecule, and what a diatomic molecule is something that goes around in pairs. So we write it like this, O2. So we can draw oxygen like this, and it's a nice kind of straight shape, which is what we call linear, because it's in a nice line. Here we have water, which is H2O, just as we did before, and it kind of draws this kind of angular shape where we have the oxygen and the hydrogen kind of sticking out at the side, and that is called angular. And then here we have a kind of blue one here. This is called ammonia, which is what is NH3. So we have the nitrogen at the start, and then we draw hydrogen. So I'm going to draw some bonds here. So I'm going to draw this as a wedged bond, and we're going to draw a dashed bond. Now they represent either sticking out at you or going away from you in the page, because they are 3D. They're not something that you can just lie flat on a page, they actually do stand up. And then the one on the right hand side here is called methane, which has got the formula CH4. And then again, we've got one sticking up and we've got one sticking out to the side. We've got the nice one coming right out the page in front of you, and then we've got one at the side. Now those 2 at the bottom have got slightly harder names. So ammonia is called trigonal pyramidal, so it's like a triangular pyramid almost. And then with your methane, it is called tetrahedral. Oops, if I can spell. There we go, tetrahedral. So I've used page 5 of the data book to have a look at different substances that are all covalent molecules, or all covalent bonding. We've got hydrogen all the way down to something called ammonia, and I've looked at the melting point of them As you can see, we've got such a huge difference. We've got hydrogen, which is minus 259. We've got carbon, that's 3,825. We've got, again, oxygen, it's minus 219. And then boron, for example, which is 2,075. This is such a huge difference. It's not like ionic bonding where they're all relatively high. So there must be something that can help us explain this huge difference in melting points. And there's two different types of covalent bonding. We've got covalent molecular and we've got covalent network, and that can help us explain the huge difference in your melting points. So the first one here, we have covalent molecular substances. They have a low melting and boiling point. What that means is they're gases or liquids at room temperature, or they're like what we call very low melting point solids. For example, water, chlorine, oxygen, carbon dioxide, they're all examples. Or what we call your diatomic elements, which we'll learn about later on, are all what we call covalent molecular substances. The opposite of that is a covalent network. So they have very, very high melting point and boiling points. What that means is they're all solid at room temperature. Because they're all solid, they have what we call a giant network of atoms kind of all bonded together. And a couple of examples are carbon in the form of diamond is a really good example. And we also have silicon dioxide, which is sand, and boron as well, just the element, which are all examples of covalent networks. So covalent structures don't conduct electricity because electrons are not able to move, so they're kind of locked in place, they're not able to move around to hold the current. However, we always have an exception, and this one is carbon. So carbon has a couple of different forms. I mentioned earlier diamond is an example of a covalent network, but we're going to talk about something called graphite. Now graphite is what you've got in a pencil, and it's lots and lots of layers kind of built up together, so when you're actually writing, you're just taking a layer of carbon off of your pencil. And because there are layers, there's kind of an end to it, so we've got little electrons here that can actually travel between the different layers and carry that current. So that's how carbon in the form of graphite can conduct electricity. So here we have a summary of all the different types of bonding so far, although I've not mentioned metallic, but I've popped it in here just so that you can have a look at it. We'll learn about that later on in the course. With your melting boiling points, if it conducts electricity and its state at room temperature. I'm going to do a little example. Here we have a table A to F with melting points, boiling points, and if it conducts, and we're going to predict the type of bonding substances A to F. So the way I do this first is I start off with metallic bonding. It's the easiest to spot because it conducts both as a liquid and a solid. If you have a look, C is the only one that does that, so we can say that's metallic. Then I go to ionic substances. They don't conduct as a solid, but they can conduct as a liquid. If you can have a look, we can see we've got B here. That is ionic bonding. And then we're left to the two covalent ones, covalent network, covalent molecular. Now the difference between that is your melting and boiling points. Covalent network sounds like it's huge, it's got really, really high melting points. So if you have a look, we can say that E is a covalent molecular substance, covalent network. And F is quite small, so that's covalent molecular. Same with A, I would say that's relatively low. With D, you could probably go either way, but I'd be more inclined to say that could be a covalent network because it is getting slightly higher than, say, the minus 183 of F. And that was covalent bonding, going back into the two different types and having a look at the shapes of different types of covalent bonds. Feel free to have a look at some past paper questions or read some summary notes just to help you with this topic as well.